Hello and welcome back. One more thing to talk about in organic chemistry, then we're done with it for now. All right, we're going to move beyond carbon, hydrogen, and maybe the halogens. And we're going to talk about what we call the functional groups. And remember, functional groups can be fun. All right, so what are the functional groups? They are common groups and arrangements of atoms that are seen very frequently in chemistry. They're very similar to what you've seen when you say, like, hey, I've got some CO3 2 minus, we call that carbonate. Because it's just so commonly seen, we call it one of the common ions. Functional groups are the same way. There's these patterns that appear so often in organic chemistry that we just kind of see them and get used to them over time. And so what we're going to talk about is the different functional groups. And all we're going to do in this case is we're just going to get a first glance at them. And in our first glance at them, what I want you to be able to do is recognize them in a skeletal formula, or talk about some of the properties of them if I ask you about the properties of them. So let's just dive right into it, and you'll see what I mean as we go along. So we talked about the alkanes as being just a bunch of carbons singly bonded to each other with hydrogens around it. But there's also these things called alkenes. And an alkenes is the presence of a carbon-carbon double bond somewhere in a molecule. And you got a molecule with several alkenes or a molecule with just one alkene functional group. So if I drew a skeletal structure of butane there, meth-eth-pro-bute, and put a double bond there, I'd be like, hey, look, all of a sudden I've got myself an alkene right there. So anytime you see these drawings and you see that double bond, and it can be at the end, it can be at the beginning, it can be sticking off the middle, right? That's fine too. We circle that guy and we say, hey, that is our alkene. So presence of a carbon-carbon double bond. Not a carbon-oxygen double bond, not any other double, but carbon-carbon double bond. Okay. Then what do you think the alkyne might be? Right, is presence of a carbon-carbon triple bond. Now, if you remember anything from your bonding and structure things, as soon as you get this triple bond, you get an orientation of the molecule where it has to be linear around that triple bond. That has to do with the hybridization of the orbitals. And so when you actually have a triple bond here, anything that's coming off of it ends up having to be linear coming off of the sides there. So if I had kind of a very simple alkyne and I drew the Lewis structure for it, it would look something like that. But it would actually also look like this around that carbon-carbon triple bond. So when you see skeletal structures showing this, you'll often see that they'll draw it straight. And so instead of drawing up, down, right, and then trying to put a triple bond in there, that's not really technically correct. People will do that. You'll see the one on the right, but more commonly you'll see the one on the left, which is they'll take it, and instead of drawing continuous lines like you've seen before, they'll actually break it up. And this breaking up is just to kind of visually verify it. This is not a bunch of new carbons in there. It's just one carbon. And so we've got carbon 1, carbon 2, carbon 3, and carbon 4. And so both of these would be the same thing as what I drew up here. This one is the most common. So when you see the triple bond, that's your alkyne, the presence of a CC triple bond. The last one on this page is what we call the aromatic. And this one is the presence of a ring with alternating double bonds. And by far the most common aromatic is a ring of 6, and you'll see some people even define aromatics as a ring of 6. I don't. I define it as any ring with alternating double bonds, because any ring with alternating double bonds will be aromatic. But by far, the most common is a ring of 6. So let's go ahead and draw a ring of 6. Right? That's a cyclohexane, but as soon as I put in alternating double bonds, it's no longer a cyclohexane. It's now got 3 double bonds in it, and the alternating single, double, single, double, single, double makes it an aromatic. And so you can actually circle this whole thing if you were trying to identify this and say, hey, that is an aromatic. Now, because this is so common, there is another notation that you're going to see where instead of drawing alternating double bonds, you just draw a circle in the middle. Why? It turns out when you have these alternating double bonds, the electrons are free to move anywhere in that circle they want, and so they do become highly delocalized, which means they do move around the entire molecule. And electrons like to do that. Electrons are tiny and they move really fast. Imagine a chihuahua, right? If you take a chihuahua and try to like cram it in and keep it in a narrow space, it's not going to be a happy dog. But if you let it run in circles, oh man, that's a happy dog. Same thing for the electrons. They really like having space to run, and it makes it very stable. So aromatics are more stable than their non-aromatic counterparts. So that's an aromatic, but like I said, we can also make aromatics out of smaller rings. That's an aromatic as well. So that would be essentially a cyclobutane with a couple double bonds, which would no longer be called cyclobutane, but it would be an aromatic. All right. So alkene, presence of a double bond. Alkyne, presence of a triple bond. Aromatic, presence of a ring with alternating double bonds. All right, our next one, alcohol, is thiols and ethers. And alcohol is presence of an OH group. So if I take any alkane and I attach on an OH group, it becomes an alcohol. And if we're trying to identify the functional group, we can just circle the OH part. You don't need to circle the whole molecule. And it's the presence of that OH group that makes that thing an alcohol. And we'll see in a little bit that there are molecules with several functional groups. Right? So we're not limited to one. We can have several. So there we go, presence of an OH group. And it doesn't have to be at the end. It can be in the middle as well. And again, I'm only drawing these shorter molecules. It can be a molecule of 100 things or 10 or 5 or whatever. You might have heard before of isopropyl alcohol. That's the rubbing alcohol that you're going to find in your medicine cabinet, and that's what it looks like. It is propyl, meth, eth, prop, 3 carbons. The iso means in the middle, and the alcohol says it's got an OH group. And so that is your isopropyl alcohol. What is a thiol? It's the presence of an SH group, which acts essentially very similar to an OH group in how you draw it and where you can put it. Okay, so there's an SH group at the end there. I can circle that and say, hey, that's my thiol, and it can occur in kind of the same places we saw with the OH. Now, here's a hint. This is the only time we're going to talk about functional groups with sulfur. So if you see sulfur in a functional group, it's going to be a thiol, just so you know. All right, the next one is the ether. What is an ether? Okay. An ether is the presence of a COC bond. So it's an oxygen in the middle of a couple carbons. And there we have an ether right there. Notice something about how I drew my skeletal structure. I did not draw a skeletal structure where the oxygen was kind of sticking off of my up, down, up, down, up, down, because then in that structure it's hard to tell. Did I mean to have the oxygen take the place of that carbon, or did I mean to have the oxygen attached to that carbon? So you definitely don't want to draw them like that because it's very difficult to tell. So what you want to do as you're drawing them is you're actually going to put a break in your drawing. So instead of drawing that, I'm going to say, hey, I need to stop here where the oxygen goes, put the oxygen there, and then it's very, very clear that the oxygen is part of the molecule. It's in between those two carbons rather than being a separate carbon. So if we were trying to identify this one, we'd be like, hey, look, I've got an oxygen between two carbons. That is an ether. And again, I could make those carbon things on either side long, huge, have other functional groups, but I've got that, and that makes it an ether. All right, the next one, aldehydes and ketones. What is an aldehyde? And that is going to be a terminal C double bond O. What does terminal mean? Terminal means the end. So it's a C double bond O at the end of one of our hydrocarbons. And so I can do that and draw it like that. That is an aldehyde. Notice that I wasn't too careful about making sure that those lines got right on top of that other one. And that's okay, as long as it's clear what your intention is. Some people will leave that space intentionally and some people won't, so you'll see both things. Now, what is also here is a hydrogen implicit, right? Because there's only 3 bonds drawn. And this is one of those times when people do often draw that extra hydrogen. It's not required, but it's not forbidden either. And so people do often draw that extra hydrogen there, but you'll see it sometimes without and sometimes with. It means the same thing because that hydrogen is there implicitly because that terminal carbon only has 1 or 3 bonds drawn from it, so it has room for 1 more. And again, this can occur, at the end of bigger molecules with other things attached to it. It's not just limited to a small molecule, but you just circle that C double bond O at the end of the molecule, and you call that your aldehyde. Now, you want to guess what the next one is? What do you think the ketone is? Aldehyde was a terminal C double bond O, and a ketone is a middle C double bond O, right? So we're going to have carbon over here and carbon over here. Whatever we want attached to those carbons, that's fine, but we've got carbon on one side, carbon on the other side. So if we've got ding, da, ding, da, ding, we can put something right there, and that would be a ketone. I've got a carbon with an oxygen attached to it, double bonded. I've got a carbon on one side, a carbon on the other side, and so that would be my little ketone, just like My Little Pony. And I'd circle that and I'd say, hey, I've got a ketone there. And that's what I'm going to have you do. I'm going to have molecules on the test, big old ones, maybe several functional groups in them, and you're going to go circle them. And there's going to be a homework practice for that, so you're going to get some practice doing that kind of thing. All right, carboxylic acids and esters. There's only 4 left, including these 2. Carboxylic acid, carbox. Okay, that's how I remember it. Carbox, and then ilic acid. What is a carboxylic acid? Carboxylic acid. It is a terminal C double bond O. You're like, hey, that's an aldehyde with OH. Ooh, that is an alcohol. What does that look like? Carboxylic acid. Ding, da, ding, da, ding. We've got our terminal C double bond O. But instead of having an H here like we had in our aldehyde, we have an OH here. And that becomes a carboxylic acid. Now, the astute among you will be like, hey, a carboxylic acid is just an aldehyde plus an alcohol. And you'd be true, or correct, except for the fact that it's not true. It's no longer an aldehyde plus an alcohol because when you have an aldehyde and an alcohol in the same spot, you call it a carboxylic acid. And the analogy I give is this. If you walk into a pizza restaurant, you don't come in and say, hey, can I have a crust sauce cheese, please? Because there's crust, there's sauce, and there's cheese. And when you put them all together, there's crust, and there's sauce, and there's cheese. But you don't call it a crust sauce cheese anymore. You call it a pizza. Just like here. Yes, it's an aldehyde plus an alcohol. But as soon as you put them together, you have pizza. And this pizza is called carboxylic acid. Okay? So don't try to circle both of those and tell me it's an aldehyde and alcohol. That's incorrect. It is a carboxylic acid. All right, so we've got a carboxylic acid there. Terminal C double bond O with OH. And then if you want to guess what an ether is, ether, that doesn't look like an E there. There you go. An ether. Well, so it's a middle C double bond O, but then, let me actually reorient this, C double bond O, which has an O and a C. Right? So yes, it looks an awful lot like an ether and a ketone, but as soon as you put an ether and a ketone together, it is not an ether and a ketone, it is an ester. Helps if you do it right. Okay, I wrote ether there originally, so if you copied that down, it's ester, not ether. I already did ether. All right, it is an ester. What does that look like? There's kind of one of the simplest esters right there. You've got a C double bond O next to an oxygen with carbon on both sides of it. And this whole thing together is your ester. And again, it can be more complicated than that. You can have din, 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 and then this. Oops. All right, so it can be big, big, long molecules, but you've got carbon double bonded to oxygen next to oxygen with carbons on both sides. That, my friends, is your ester. All right, 2 more and we're done. All right, amines and amides. N. Amine is the presence of N. So anytime you see N, you think you have an amine. The exceptions will be the amides, which we'll talk about in just a moment. So it can be an N with 3 carbons attached to it. It can be an N with a hydrogen and a couple carbons attached to it. It can be an N with a couple hydrogens and a carbon attached to it. That's fine. This is the presence of that nitrogen as a central atom somewhere in your molecule. So what does that look like? There's a simple amine right there. I've got a couple carbons and I've got the NH2. Remember, if I'm drawing this, I have to write NH2 if that's what I have, because NH might also be possible, or N might be possible, depending on the chemistry we do. It would be charged, it would be an ion, but it's also possible. Or if we wanted to make something that was in the middle of the molecule, I could make that. And there, it would have 1 hydrogen, so I'd write NH. Or I could make it where I've got 3 things attached to the nitrogen and no hydrogen. That's fine. Anywhere you've got nitrogen, you're going to have yourself an amine. The difference with that and an amide or amide, I've heard both. I think amide more often. The difference between those two is that the amide is a C double bond O next to N in the middle of a molecule. And so for an amide, what you're going to have is an O here with an N and maybe an H2. Right? The N can be attached to whatever it wants. It could be more things. It could be 2 hydrogens. It could be 1 hydrogen and a carbon, whatever it is. But I've got a C double bond O next to an NH2. That's my amide. How do you tell the difference between an amine and an amide? You look for the presence of that C double bond O. And in fact, that C double bond O is the thing you're going to be looking for not only in the amine and the amide, but also in the carboxylic acid, also in the ester. That C double bond O next to something is your indicator that you have one of your pizza groups. The amide is a pizza group, the carboxylic acid is a pizza group, and the ester is a pizza group. C double bond O next to an existing group that we already know, either alcohol for the carboxylic acid, ether for the ester, or amine for the amide. What we're going to do next is we're going to do a bunch of examples so you can see this in action. And I picked these molecules that we're going to do examples on because they're actual real molecules in the world. And our first one is lycopene. If you go buy a bottle of ketchup, it tells you antioxidant power. Yes, of course it does, because tomatoes have a lot of antioxidants in them. Naturally, it's not like ketchup's special. Eat a tomato if you really want the natural antioxidants. But what do you see in here? Right? Oh, let me blow this guy up. What do you see? Nothing, because it disappeared, because it's Microsoft. There we go. What do you see? Oh my gosh, look at all those double bonds, right? So this one has a ton of alkenes. And in fact, on a test, I would never give you lycopene because it's way too many alkenes. On a test, I want you to circle every single functional group. Here, I'm not going to because there's so many of them. It might look like you have an aromatic there at the end, but it turns out you don't because it's not connected and it's not alternating double single bonds anyway. So there is an alkene, or a bunch of alkenes. This one, my molecule, I love this molecule. If you like to see, I don't know why I can't blow things up today. If you like to see, this is a great molecule to have in the back of your eyeball. It's called cis-retinal. And what cis-retinal does is it gets hit by light, it rotates, turns into trans-retinal. That signal and energy gets processed down through your optic nerves in your brain, and you see things. So it turns out everything you see in the world comes from rotation of a bond. And we talked, I think, about the kinetics of this way back at the beginning of the chapter, that if you just let trans-retinal have to relax back to cis-retinal, it takes about 400 years, 500 years, and so it just doesn't happen very quickly. But as soon as you put an enzyme in there in the back of your eyeball, the sole job is to take transretinal, put it back to cisretinal so that it can receive another photon and you can see again. It happens in fractions of a second, about 150th or so of a second. Crazy fast. So really, really neat stuff. What do we see in terms of functional groups? Again, you see this one here and you're like, oh, is that an aromatic? And it's tempting. It's got the alkene in it, but what it doesn't have is the alternating one. So yes, we do have a bunch of alkenes here. And again, I wouldn't give you this molecule on a test. It's really big. What do we have at the end? We've got a C double bond O at the end. So we'd label these guys alkene, and we're going to label this one aldehyde. My computer is no longer keeping up with my writing, so if I crash in the middle of this, we'll know why. All right, our next one, we're going to identify our functional groups in here. Again, things to look for in functional groups, right, are oxygen, nitrogen, sulfur. Anytime you have oxygen, nitrogen, sulfur, you've got a functional group. You just got to figure out which one. So every single oxygen, every single nitrogen, every single sulfur should always be labeled, circled, whatever I have you do in your molecule as part of a functional group. Double bonds, triple bonds are always going to be part of a functional group as well. In this case, we've got a bunch of double bonds in there, but they are part of an aromatic. They are not a bunch of double bonds. Aromatics are also a pizza kind of thing. It's not 3 alkenes. It's now an aromatic because they are arranged in a way to make this new thing, which is our pizza. We do have our alcohol over here. And what do we have here? Is that an aldehyde or a ketone? Well, we do have a carbon after that. That makes it a ketone. Why did I show you this molecule? I showed you this molecule because this is the smell of raspberry. And it turns out the smell of raspberry for a naturally derived source is one of the most expensive odorants in the chemical odorant industry. A kilogram of this stuff will set you back about $25,000. Why? Because the raspberries don't have a lot of it and it's really hard to extract. Now, could we synthesize this? Yes, but in terms of natural raspberry smell, very, very expensive. So if you have anything that's ever naturally raspberry smelling, you probably paid a whole lot of money for it. $25,000 for a kilo. Crazy. All right, your next one is your Starbucks smell. So this is one of the primary odorants, it's not the only one, but one of the primary odorants in the smell of roasted coffee. So we're going to go ahead and look at this one. It's very tempting to circle that guy and say, hey, we've got an aromatic alternating double bonds, but it's not. You can't have an odd number of things in your ring and have alternating single double bonds. There's 2 single bonds in a row here, so that's not an aromatic. However, these are both alkenes. That oxygen is between 2 carbons. Yes, it's part of a ring, but it is still an ether. And the SH, we know that one because there's only one thing that involves S, that's our thiol. All right, the next one is yeast. So if you like breads that are very yeasty, or if you are one who likes beer, no idea why you do. But if you're one who likes beer and you like kind of a yeasty strong beer, this is probably one of the things you like about it. What do we see? Now, I'm going to tell you, I chose natural products, and so this one, I would never, ever, 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 ever give you this one on a test because there's 2 overlapping groups. Never see that on a test. Don't worry about it. What do we have? We have this group over here, and we have this group over here. Remember, every time we've got that double bonded oxygen, we need to look on either side of it, see if it's one of our other groups. So I've got a double bonded oxygen with an oxygen, that's my ester. I've got my double bonded oxygen with my nitrogen, that's my amide. And again, those are overlapping, so it's not technically what they are. Never see this on a test. I just thought it was an interesting molecule to look at. All right, last one. For those of you who my class has driven to drink, this is one of the primary flavors of a Cabernet Sauvignon. So if you're a wine person, you might know what a cab tastes like, and this is one of the primary flavors in it. What do we see? We do see the aromatic in this case. Now, in terms of this aromatic, there's also some amines, and I would never give you this one on a test because I would never give you overlapping groups on a test. So don't worry about overlapping groups. you won't see overlapping groups other than our pizza groups, our carboxylic acid, our esters, our aromatics, and our amides. What do we have here? What's on either side of that oxygen? Well, if you look over to the left, it's an unlabeled endpoint, which is a carbon. If you look over the right, it's a carbon. And so this one is an ether. All right, that is the end of our foray into organic chemistry. I hope you learned something new, and have a wonderful day.